Hi everybody, welcome to a Purdue Space Program Liquids livestream. Tonight, we will be performing CraterMaker Special's Full Duration Hot Fire. We are currently at Zucrow Labs in West Lafayette, Indiana, the largest academic propulsion lab in the world. I'm Shelby, I'm a sophomore in aerospace engineering, and I'm a propulsion engineer on the team.
And I'm Ian, I'm a senior in aerospace engineering, and I'm the technical director for PSP Liquids.
The test we are conducting tonight is our full duration hot fire, which is a flight-like simulation of our propulsion system. We are going to fill CraterMaker Special with its propellants and ignite them in the rocket engine's combustion chamber to create a little under a half a ton of thrust. The rocket will be held down by a support structure, and we will be able to measure the thrust of the engine. The goal of this test, as with all of our vehicle tests, is to collect data, and to do so, we have over 20 sensors transmitting data to our test conductors.
This hot fire is one of the last remaining milestones on our pathway to launching CraterMaker Special in the Mojave Desert in California coming soon. We've had some issues with past hot fire attempts recently, but we've worked through them the best we can, and we are going for an attempt tonight. Recently, we have figured out a propellant conditioning issue, which has prevented us for a couple of attempts, but we're back at it again tonight. And let's get some views from our courtyard, which is our testing area at Zucrow, where we conduct our hot fire tests and other cold flow attempts. We've begun propellant loading, which means we are actively loading fuel onto the vehicle. Before starting our stream tonight, we already loaded up our oxidizer, liquid oxygen, onto the rocket, so we're almost ready to conduct our hot fire attempt. Later on, after we load on our methane, liquid methane, we will be loading on gaseous helium into the very top of our rocket where we store our pressurant. The pressurant is used to force our fuel and oxidizer through our plumbing and into our combustion chamber at the very bottom of our rocket to perform our hot fire. This will generate thrust, which we will be able to read on our GSC equipment and be able to record the data. Let's get back to our courtyard.
As you can see from those views of the courtyard, there's a lot of venting happening. Ian, would you like to talk about what's happening in the courtyard?
Sure. So the reason why you're seeing this vapor, these clouds form around the rocket, is because of the propellants we use on CraterMaker Special. Both the liquid methane and liquid oxygen are extremely cold. They're around, negative 300 degrees Fahrenheit for the liquid oxygen, which is cold enough where it boils off automatically at ambient temperatures.
Got it.
So that boiling phenomena produces that vapor, which is then, exits out of the rocket during propellant fill, and then you see it at the exits of our propellant vents. So that's normal for us, that we're just loading on propellant to the vehicle, and the result is we have this vapor forming on the outlets of our vents.
Got it. Very cool.
Glad to clarify.
So, Ian, what's a water deluge?
So a water deluge it's a ground support equipment, which also stands for GSE. So it's a ground support equipment that we use to protect, the concrete and the infrastructure we have by the rocket chamber. So we produce a lot of thrust and a lot of force and heat because we're shooting hot gas out of our chamber and down into concrete. And we want to be able to protect that concrete so it doesn't get damaged. So we have a thing called the water deluge, which shoots out water at high pressure against a metal plate to kind of help deflect and take away some of that energy that otherwise would have been, lightsabering into the concrete.
Oh, yeah. Okay, cool. Do we know when about like the water deluge starts?
Yeah, it starts usually a few seconds, about, 10, 15 seconds before the hot fire. So when we go for our attempt, you'll start to see a lot of things happen in rapid succession. That's because we're running our auto sequence. So pretty much once we get close to hot firing, we hit a button and then the rocket kind of takes care of itself more or less and runs through a bunch of operations. And one of them is starting up the deluge. And once that gets started, it's only a few seconds away from lighting the engine.
Very cool. Very cool.
And you're actually helping design the next iteration of our water deluge, right?
Yes, I am. So for our Pathfinder rocket, we actually have a whole GSE team that is building up a launch trailer. And I'm actually working on designing the water deluge for that. So it's a little bit of a smaller scale engine, but it's pretty cool.
That's really cool. Yeah, a lot of cool stuff you can do with ground support equipment. And very excited to see how this water deluge performs tonight.
Yes, me too.
Yeah.
We are currently holding the T-clock to let our methane dewar build pressure. Ian, would you like to talk a little bit about that?
Sure. So we fill our liquid methane tank on the rocket from a large storage container that holds liquid methane in the courtyard. And it goes through our Black Cat launch system, which is some more GSC that we were talking about that controls filling the rocket with our propellants. So right now we're letting that that large liquid methane storage container pressurize, so build pressure. And that's done by having a small amount of that liquid methane pass through a heat exchanger, which lets it vaporize into a gas. And then that gas is able to build pressure, which we use to force that methane into the rocket through all of our ground support equipment.
Yeah, because it's that change in pressure that puts it on the rocket, right?
Exactly. We need some amount of pressure difference between inside of our rocket and in that bulk storage container to allow flow of liquid methane into the rocket. And right now we just have to let it build up some more pressure, let it vaporize some more methane into gaseous methane. And until then, we're going to have to hold as we wait for that process to continue. It's kind of automatic. It does it on its own. We just have to wait and let it do its thing.
Yeah. So anyway, while we're waiting, we're going to hop into some other content for y'all. So testing CraterMaker Special did not just start with this full duration hot fire. We have been putting CraterMaker Special through many major tests, including cold-folds, which is similar to a hot fire, but instead of using combustible propellants like liquid methane and liquid oxygen that we're going to use tonight, we use inert liquid nitrogen. Those cold flows let us dial into our procedures without needing to run the rocket engine. Here's a quick video highlighting some of those cold flows that we have ran recently.
All the cold flows we've ran in the past have provided us with a ton of useful data that has informed us for the test we're performing tonight. Now, as we get closer to, letting that dewar press up, let's get some more views of the test area so you can see what's going on. You might have saw a little bit of action there. We just had a little bit of water flow through our deluge that we were talking about earlier, just as a little preliminary test to make the most of the time we have right now as we wait for that LNG liquid methane dewar to begin pressing up as we prepare to fill propellant and fuel into our rocket.
Welcome back to our stream. We have a very special guest joining us right now, one of our prop leads, Gabriel Martino.
Hey everyone, I'm Gabe.
Yeah, you've been with the team for quite a while now, and you're leading our propulsion team along with Arjit, who we interviewed a few streams ago. Can you tell us a little about what you do on the team and what your role is?
Yeah, I am the co-propulsion lead with Arjit, like you said. Been on the team a little more than a year, maybe a year and 3 months now. I initially started working under this wonderful gentleman on the pump team, so our electric pump development, which has really picked up. Since then, I've been leading it and have now converted to the overall propulsion lead and have been owning some design of the injector and other projects here and there.
Very cool. Nice.
Very awesome. So, Gabe, what's been your favorite memory on PSP?
Good old Saturday morning work days with Ian.
Oh, yeah?
A lot of fun.
Yeah, for those who may not know, we have work days every Saturday with, the whole Liquids team to get together and work on our problems and, do engineering together in a group space, in a group setting. It's always a lot of fun.
Yep.
Yeah. So you're working on Copperhead, which is the next vehicle that we're working on in conjunction with CraterMaker Special. Can you tell us a little bit about what makes that rocket special from a propulsion standpoint?
Yeah, for sure. Copperhead is a pretty big developmental increase in technical challenge and rigor from CMS or CraterMaker Special. CMS has a blowdown architecture which allows us to pressurize tanks given a higher upstream pressure, and we're using a control system called Bang Bang. I'm not gonna. Should I dive in too much?
Yeah, sure. Give us a little bit about that.
Bang Bang essentially is you have two set points for your pressure, which you cannot go below and you cannot go above. And you have a solenoid valve, which is either open or closed, bounce between those, and we call it banging between those. And that's how we set the pressure in the tanks. So Copperhead's doing away with a lot of that work, and we're actually going into a servo regulator. So it's an actively controlled regulator to control the pressure in both tanks. And then after those tanks, we're getting yet another pressure increase by a set of electric pumps, which are another device that puts us a little bit closer to orbital rockets, which I am personally very excited about because it's been my little project. But yeah, I mean, there's a lot more rigor that comes with just the pressurization system alone. And then on the engine side, we're actually switching from ablative to a regeneratively cooled engine, which is additively manufactured, which I'm very, very excited about. And then for our combustion devices, we've changed from a coax shear swirl injector to a liquid co-swirl, which many of us are excited about, which we are heading into a dev campaign very soon. So excited to see some testing of our injector design and see if things work out.
Yeah, seems like a lot of excitement going on.
Yeah,
it's really cool.
Yeah, exciting stuff. So we've been asking everyone we've interviewed on the stream how high they think CMS is going to go when we launch it. What's your prediction?
If I had to guess,
Down to the foot.
Down to the foot. Let's say 15,111 and 3 inches.
And 3 inches,
Ooh.
okay. Well, that's certainly the lowest we've heard. So maybe a bit conservative, but, great to hear that. We'll put you in the betting pool, and we'll get back to you if you hit the jackpot.
Perfect.
So you talked a little bit about our propulsion system for Copperhead, which is the next rocket. And you've done a lot of work with CraterMaker Special, especially during ops like tonight. Can you talk us through, what you do during these operations where you're out at Zucrow working on CraterMaker Special, getting us towards hot fire?
Yeah, I essentially am responsible for the propulsion system at the moment. So we have all the design has been finished. It exists in hardware. So operationally, I have to oversee our igniter prep and oversee the pyro actuation method. So we really have black powder charge that actuates our run valves, and then a solid grain igniter slug that sits in our chamber via a plug. So I oversee the setup and conditioning of those two devices, and then I sit as an advisor in the control room for operations and overall system status.
That's really cool. So you mentioned the pyrotechnic actuator and the pyrotechnic igniter.
Yeah.
So those are two different things, right?
Yeah.
Cool.
I'm sure you could talk a mighty sum about the pyro actuator as you initially designed our first iteration.
Yeah, a long time ago, I think about 2 years, an old version that isn't currently being used, but the one we have on now has proven to be quite reliable over its test campaign. And,
Yeah.
it's a piston-based system that basically has that little pyrotechnic charge in it. And then once you light it off, it generates a lot of pressure, and that pressure is translated to a force, and it rotates our ball valves, which are what we use to control flow from our propellant tanks into the combustion chamber. So, and then you, of course, are in charge of loading it up and getting it ready to fire.
Yeah.
It's pretty cool to see you get that set up every time.
Yeah, we have to be pretty careful working with black powder,
Of
and
course.
especially a solid propellant, which is cool. We're using small commercial off-the-shelf rocket engines to light our much larger liquid rocket engine. So it's a cool little rocketception there. But yeah.
Great way of putting it.
Pretty cool. So, back to like more of a general question. What's your favorite part about being a Purdue student?
Oh, I think Purdue is a great school. I'm actively trying to sell my younger brother on it. I think as a university, Purdue offers anything your heart could possibly desire academically, and then as far as clubs go, I think that's really where Purdue shines amongst the other top engineering schools. We have clubs for every possible technical skill to flourish, and I'm a big fan of everything that's offered here, especially PSB. I know for those who don't exactly like rockets, there's a immense amount of racing teams, and then really any other niche engineering topic you could possibly want. So yeah, I love the clubs here. I'd say that's a tough sell.
Yeah, I agree.
It's good you're trying to get your brother over here.
Yeah, we'll see how that works out.
Have you ever, what's your take on internships? Have you ever had one, and what'd you get out of that experience?
Yeah, so last summer I was working for the Starship Heat Shield team, not
Two different
Starshield.
things,
Yeah,
yeah.
two very different things. Out at Cape Canaveral, Florida. I had a lot of fun, and I can safely say that this club enabled me to go and take that step and work over there, which I absolutely loved. So this upcoming summer, I'll be returning to the Raptor Turbomachinery team. So back to SpaceX, new team. Very excited for the opportunity, and I can't say like how instrumental PSP Liquids has been in that. So big fan of the team, and I'll be around for a while.
Oh, good to hear.
That's awesome. Exciting stuff.
Yeah.
Yeah.
How about this? We have a lot of traditions here at Purdue. Do you have any favorite ones? Doing a fountain run maybe, or?
I really like, so we have a set of fountains here for those of you who are not students or alumni. And one of them is the Lions Fountain, the 4 lions. And there are 4 potable streams of water that anybody can drink from. So it's good luck to drink from it before an exam. And I really enjoy going up to that fountain in the freezing cold and drinking some ice water before a rigorous exam, as always.
And as a Purdue engineering student, you kind of need as much luck as you can get.
You really do.
Oh yeah, I think we both know that.
Yeah.
We do.
So one of our big emphases in liquids is learning. So I have kind of a crazy question. What's the most random thing you've learned from being a part of this team?
From being a part of this team, I don't know. It's tough to tell. It's a lot of weird niche engineering knowledge. I wish I didn't know as much about fatigue life as I've come to learn in the last couple weeks, but yeah, universal slopes is pretty cool.
Well, you mentioned the electric pumps that we have coming in on Copperhead. And you did a lot of work on those in the past year. Can you explain where we're at in the process and what we're trying to do with them? What is the end goal of that system?
Yeah, so we are actively designing and getting towards the first electric pump fed regen engine PSP has ever done. And currently in the design process, we are at in between the preliminary design review and the critical design review phases. But because this is the first time for a lot of us, we have opted to take a test heavy campaign. So we are making development hardware on all fronts. We're making a calorimeter to test our heat flux for our regen system. and to test a subscale multi-element injector to test injector design methodologies. And then we are also making development hardware called the battleship pump. So we are making a fuel and then following a LOX pump, liquid oxygen, which we will use liquid nitrogen initially to test. And these are very modular designs, very little mass optimization, if at all.
Sure.
But to maximize the information that we can get without actually building up a very expensive system that could fail and bring other pieces with it. So we're kind of expecting for this development LOX pump or fuel pump really, to fail in quite spectacular fashion. As we gain more information, take Starship as an example. You got to break some stuff to learn, and very excited to see how that goes. But as far as where we are in that, we have already made multiple pieces and are actively finalizing the design of our seal cases while we are finishing the manufacturing of our fluid systems. So a lot of stuff, and our ground system that we've had to build up. Actually, we've made we have made 2 sets of new ground support hardware to enable us to make pumps. We've made a balancing rig that has been cleverly named Yoda.
Can you explain what that is?
Yeah. Actually, that's a good point. So when you have something like a turbine or a turbo pump, or really any fast-moving turbo machinery, any fast-moving thing at all, if you take your tires, when you take your tires to get a rotation or change them, they put it on this little scale that spins it, finds where there may be imbalances, and they load weights on the inner rim of the tire to counteract that imbalance. So that allows you as a driver to get a smoother ride as you drive without so much imbalance in your wheels, which results in some oscillation as it rotates. So for us, the same principle applies. We have a certain imbalance when we machine these components, especially since our spinning assembly is multiple parts that fuse together. We want to mitigate that. So what we do is when we assemble the rotating assembly, we have a stand called Yoda, which is a set of accelerometers on a freestanding body. And we can measure the oscillations and actually pinpoint where they are in terms of like radial position or clocking on the rotor itself. And we'll remove material as needed to get to a better balanced state. We have certain standards that we hold it to that are followed by industry, and that allows us to spin up to our 30,000 RPM and hold without crazy instability or imbalanced frequencies spreading across our fluid system or our structures. So very, very important. And then our other piece of GSE is our test stand called Harbor, because a harbor holds ships. So very clever naming scheme there. And we basically built this to test our battleship pumps without needing I think you guys have already talked about Celsi or Condor.
Not extensively.
Not today.
We'll get to that at some point soon.
Okay.
Don't worry.
So our big test stand with a lot of expensive hardware, we would like to get testing sooner than that is actually ready. So we've come up with a design for converting the hardware that controls the rocket that we're actively testing, CraterMaker Special, and using that to do preliminary pump tests on the battleship hardware. So very exciting time, things that we're doing to accelerate the development here at PSP.
Yeah, seems very, hardware heavy, a lot of stuff going on across the board when it comes to that project. It's very exciting to see hardware start to come out of the design work. And we actually talked to Carrie, our manufacturing lead, not too long ago about that process of machining some of your impellers for battleship pump. Really cool to see that process.
Yeah, I cannot say how instrumental Carrie has been in our development. The guy is incredibly good at what he does, and we could not be hitting any of the deadlines or targets that we aspire to hit without him. So shout out Carrie, that guy's a G. But yeah, I'm very excited because we've been staring at CAD for a long time here, and we're finally getting some hardware you can hold and see the scale. And
testing coming soon.
Yeah, very, very soon.
And I'm sure we'll have some amount of media coming out of when that happens of tests being successful and all that.
Yeah, absolutely. Hopefully.
Something to look forward to for sure.
Yeah. Kind of a follow-up question on all of that. What do you think the most challenging part of that is?
It's this is very, very new endeavor for us and really for Purdue, as there are not many professors that have research in radial turbomachinery, specifically turbo pumps. So it's a lot of figuring out what we do not know. That's been a big risk that we take whenever we step into design reviews. We do some analysis, but we really don't know if it's the right analysis to take. But with the help of all of our industry partners and the many talented faculty advisors and professors that we have at the school, we've been able to come to a pretty decent design, I think, and we'll find out how well it works very soon.
Very
Exciting.
cool.
Very
Nice.
cool.
So we talked about our pumps. You also mentioned earlier we have a really cool chamber that we're making.
Boy.
A lot different from CraterMaker Special's ablative chamber, which we had Arjit talk about earlier on in other streams. Can you tell us about what we're doing for Copperhead and what makes it so interesting and so different from CraterMaker Special?
Yeah, for sure. Ablative cooling, as Arjit may have said, is the process of using an ablative material or something that is essentially sacrificial that creates a boundary layer to insulate from the very hot combustion gas to the outer wall by creating some gas layer of disintegrating material. So this is a inherently sacrificial and non-repeatable system. So to give you guys a good example, the current flight chamber is sitting in my bedroom.
Okay.
And the hot fire chamber is sitting on the vehicle right now. And we cannot use the two, we cannot use one. And that puts a lot of strain on manufacturing, specifically when you have variances from part to part. So ablative inherently is a non-repeatable, at least the way that we make it. It's very difficult to repeat the exact tolerances of the material relative to something like additive manufacturing or traditional manufacturing. So when we have sacrificial chambers like we do on CraterMaker Special, we have to deal with some certain invariance in our chambers thicknesses, some of the dimensions here and there. We get it pretty good. We use a mandrel setup, and there's a very cool YouTube video on how we wind it by our former propulsion lead, Andrew.
Yeah, and why don't we actually cut to that video right now so you have a bit of context?
Sweet.
Hi, my name is Andrew Neri. I'm a junior in aerospace engineering, and I'm the PSP liquids propulsion lead. So currently, we're working on winding our combustion chamber for CraterMaker Special in carbon fiber. This is an ablative combustion chamber, meaning the inside liner is made out of a very high temperature material designed to slowly erode and carry away combustion heat as the engine burns. That liner, though, however, is very brittle, so to provide structural strength to withstand chamber pressures from combustion, we wrap the outside in carbon fiber. This is done with the filament winder that we designed and built in-house, including all the software. So we manufacture the entire engine, including the ablative and the filament wind in-house.
So that was a quick video going over what you were just talking about. So yeah, what does Copperhead do it?
Yeah, so instead of using that ablative method or any hand wound, a lot of manual machining has been kind of eliminated. We've switched to an additively manufactured regen engine. So what that means is we've found a way to, well, scientists many years ago found a way to cool your chamber, which is a very, very hot system, by running some of your propellants, namely fuel, very commonly, and in our case, running fuel through channels in the actual walls of the chamber to keep the temperature of the material lower. So you're taking some of that combustion energy that would have otherwise been transmitted into the material, and you're taking that into the propellant, which actually helps your combustion as well. So it's a neat thing, and it's very helpful. And the beauty of it is it's reusable. So we'll have a chamber that can be additively manufactured, which is metal 3D printing, and in our case, that is powder bed fusion. So we're making a powder bed fused, chamber out of Inconel 625.
Oh.
And we'll be able to fire it multiple times. I think our current testing plans show a maximum of 10, but we have a pretty big factor of safety on that. And we have, I believe, a cycle lifetime close to 40 fires. So won't have to throw those chambers away. And we will not be wanting to machine more than one of those. So
That's super exciting. So I know we mentioned it a little bit earlier, but we have a test cell that we're building up Condor for that. So how is Condor going to be able to help with the test campaign for this?
Oh,
engine?
That's a great question. So this is a much more complicated system than what CraterMaker Special has, and with that, we are taking a lot more risk. So with that, a way to mitigate that risk with a lot of unknowns and a lot of moving parts is having a cell such as Condor, which allows us to test without the vehicle. So the propulsion team, namely me, RG, and our members, can move a lot faster without relying on the rest of the vehicle to be fully designed and fully built just for us to get to our first initial tests. So it's a great developmental upgrade. This is something that isn't just for Copperhead. It'll go for years to come. Hopefully, every engine for the rest of PSP's life will fire on this stand until they eventually upgrade it. But it allows us to fire the engine and get really, really good vital test data without having to integrate it to the vehicle. So ideally, once we have our vehicle ready and our propulsion system ready, we go through a qualification campaign when everything is mated, and then we should be good to launch. Very excited about that day too.
Yeah. So it's like a whole new test infrastructure that we're building up here.
Exactly.
And it's pretty industry standard too. It's very similar to what companies and NASA use to test engines that they're developing, which
Absolutely.
is really great for helping members of PSP Liquids get experience that they need to transfer over to working in the field.
Yeah, I agree.
How would you say PSP Liquids has helped you as an engineer?
Wow. So I would say one of the biggest things that Liquids has given me and a lot of the members that I see is it kind of bridges that gap from the theory that you learn in class to real hardware and definitely tests. You gain an incredible amount of information and experience in testing and qualifying your designs that you wouldn't normally get just by doing classes. So although classes are very good at what they do, at times you have clubs like these which really show you that end-to-end process of, you get this design, you get it to a manufacturing state, then from manufacturing you get it to a qualification state. You can test and see how well you designed, and then you can keep going through that loop till you get that perfect design you're looking for. So yeah, it's a very exciting thing that you get to see almost every day that I think I take for granted. So, yeah.
So not just, how to design something, but also, the process that you have to go through for making rockets and making large engineering systems.
Yep.
Yeah.
Absolutely.
Cool.
Yeah, so kind of talking about classes, what's been your favorite class that you've taken here at Purdue?
Actually, I really enjoy one of the classes that I'm currently in, aerodynamics. Me and Ian are taking that together.
Yeah.
And we've gotten to the good part, which is isentropic compressible flow in nozzles, which has been a lot of what I've done, which I find very entertaining. Although, Kenito, if you're watching this, I pray you don't keep hitting us with homeworks that you've been hitting us with, but I love the content, and he's a very good professor. So, yeah just makes those homeworks a little bit rougher.
Yeah, definitely a great class.
Yeah, great class.
Well, I think we have one more question for you here, Gabe. If you're talking to the future members of PSP Liquids who are maybe in high school, maybe in middle school, what would you tell them, and how would you convince them to come to Purdue and be a part of PSP?
Yeah, I think PSP is probably one of the strongest cells for Purdue. As far as when I was coming in, seeing students as young as like fresh out of high school, starting your college career, and getting the ability to get your hands on a liquid rocket is truly special. And we couldn't do it without the infrastructure that Purdue as a university supplies us, but also with the alumni and the upperclassmen students that we have that hand over this immense amount of experience that they've gained. So I think it's really, really something to dig into. And for all future members, I'd say come to the club and give it your best. And I promise you, it's the time in you put. If you want to chill and just hang out with us, we're a pretty cool group of people. But if you want to become some really good engineer, I'd say put in the hours and you'll get out what you put in.
Yeah, definitely a once in a lifetime experience being both at college and on PSP Liquids. I think it's for sure something we all cherish.
Yeah, for sure. Well, thank you so much for joining us.
Of course. Thank you guys.
Yeah.
All right, let's go 30. So I hope you enjoyed that interview with Gabriel.
Yeah.
He's one of our propulsion leads. He's done an amazing job on the team. And just for some more info on our hot fire attempt tonight, we are still holding. We are having good progress on our propellant pressurization. The liquid methane dewar is performing well. We're
Yeah.
seeing good response on the pressure build on that system. And we are still holding, as I said, but we are hopeful that we will be able to get up to the needed pressure we need to continue liquid methane fill.
Yep. So continue to stay tuned or not. As Gabe mentioned, we manufactured our impeller in-house, and actually nearly all of CraterMaker Special is manufactured by students here at Purdue University. And our upcoming rocket, Copperhead, will be comprised of some of the most complicated and advanced parts that we have ever made. Let's hear from our manufacturing lead, Carrie, as he machines the impeller prototype for our electric pump system for Copperhead.
Everyone, I'm Carrie. I'm a junior in aerospace, and I'm the manufacturing lead for Purdue Space Program's liquids team. And I'm currently working on propulsion's impeller. This impeller is actually going to be made out of stainless steel, so this is going to be the real deal for testing. And what I'm currently running it on is the VF2 at Bechtel. The VF2 is an absolutely amazing machine. I've run this machine for countless hours, even 18 hours all at once. This machine can do a lot. So let's get running.
We are excited to get into the hardware and test phase for Copperhead, so stay tuned for more Copperhead updates on our Instagram, LinkedIn, and X, and right here on YouTube, so make sure to follow us there at Purdue Sets.
And we're going to cut back to more views of our courtyard as we continue to wait for our liquid methane dewar to pressurize. as you saw a little bit ago, we're pulsing our water deluge, which we talked about earlier in the stream. So that means we're just turning on and off our water supply to that piece of ground support equipment to do some testing on it, seeing good response from it luckily. So everything is behaving there. Basically what that system does is we have a high pressure water supply hooked up to a valve, which we can pneumatically actuate, which means remotely in the control room, turn on and off and control the supply of water going to our water deluge. And that high pressure is able to push out the exhaust of our engine once we start the hot fire and deflect some of that heat, some of that hot gas away from the ground to, diffuse it, cool it down, and prevent damage.
Yeah, so we just want to check to make sure that that system's still working here tonight. So. Hi everyone, welcome back to our stream again. I'm here with Mahir, one of our avionics leads. So, do you want to kind of talk about what you do on this team?
Sure. So I lead the hardware side of the avionics. I'm actually a CS major. What that means is, although I came in here doing software, I wanted to do a lot of hardware on the team. So that allows me to do like PCB design, um, designing different parts of, for example, we have a battery, we have to step down the voltage for the different systems. We have to integrate the like pump, like ESC for the pump, understand the motors, and yeah, so basically everything pertaining to the electronics of the rocket.
Okay, very cool. So, what's been your favorite like piece of hardware that you've worked on?
So in the past, we had a custom PCB for Copperhead, and although we switched out for a Raspberry Pi, I've gotten the chance to do the same thing for Copperhead. So we use a custom designed PCB with a STM32 microcontroller, and then a bunch of different peripherals for reading sensors. So we have a sensor or a chip to measure thermocouple, TC, which is a TC, RTDs, which is a resistance temperature detector, as well as other temperature measurements. And then we also measure the pressure transducers through an ADC. And then this allows us to control the pumps based on a pressure signal from downstream.
That's exciting stuff. So, are y'all gonna be able to like test that and integrate that at all, like before we build up the whole rocket?
Yeah, totally. So we have, as I think other people have mentioned, we have Cell C or Condor, where we're going to do a subscale testing off the rocket, and then that'll allow us to validate the pump, just testing like the pump control loop. So say if we have a set pressure set point, we want to control the RPM. If the pressure is too high, we can decrease the torque, decrease the RPM, and kind of make sure that we're operating in our ideal margin the entire time. So that'll be our first step, and then once we start integrating that, once we've validated that, we can integrate other parts of the rocket, including like upper press systems to pressurize the tanks, and then keep the downstream like the pump with a proper like inlet pressure. And then yeah, so we'll take it step by step. The first one is obviously testing pumps in Condor, and then we'll go on from there.
Super exciting stuff. So, what's been your favorite memory on PSP Liquids?
Yeah, so I'll go back to sophomore year. So I've been in this team since like freshman year, and in that semester, we kind of were handed the test campaign for CMS. So we had to, get the rocket ready for cold flows. So we had like our integrated test system. There were a couple issues which we had to spend a lot of time debugging, but it taught me a ton about electronics debugging and how to not fail my classes while doing a lot of PSP. So I think that semester taught me the most, and it was kind of a trial by fire, but it still allowed me to learn a lot, and I'm kind of grateful to that to this day.
Yeah. I can't remember if we asked you this the last time we interviewed you, but how high do you think CMS is going to go when we launch it?
I think last time I said around like 30, 35, 34,000 feet. I know we had designed it to be around 30,000, but that was with a little conservative estimate, so I think it might go a little higher than that.
Yeah, you still think it's going to go that high?
Yeah.
All right, very cool. Well, thank you so much for joining us, and we're going to cut back to some more views of the courtyard.
Sure, thank you.
We are pursuing a fuel fill. We had good response of our liquid methane dewar. We got up to the needed pressure we needed to begin that fuel fill. LOX is still good. We might top off for a little bit just to make sure our tanks are full from there, but we are continuing on with this hot fire attempt with filling liquid methane onto the vehicle.
Yeah, so let's cut back to some views of the courtyard while that happens. PSP Liquids was founded in 2017 and started development on our first rocket, Boomizoomi. While Boomizoomi did not make it to flight, its successor, Boomizoomi B, was developed and then flown 3 times, including twice in one day at the Friends of Amateur Rocketry FAR site in California. Liquids then set their sights on CraterMaker Special, which is the rocket we are testing today. CraterMaker Special, as we've mentioned previously, is fueled by liquid methane and liquid oxygen. It uses an ablative chamber that we manufactured in-house. As for the future of liquids, we have set our sights even higher. Our next rocket, Copperhead, will have a regeneratively cooled electric pump-fed propulsion system with a coax swirl injector. That's what Gabe talked about earlier. And the tanks will have active pressure control, then the composites will be made in-house. We are super excited to continue development and to start build on this rocket soon. Let's get some more scenes of the test area as the propellants are loaded onto the vehicle.
We have a bit of a change of plans tonight. Unfortunately, we're not going to attempt a hot fire, but we are going to continue testing our propellant fill system to get more data in preparation for a full attempt coming soon. So that means we're not going to hot fire tonight, but us at Purdue are going to continue our testing campaign to characterize our propellant fill system.
Yeah. So with that, we will be closing out our stream here. We'll be getting back to hot fire testing as soon as we can, and we look forward to having you back with us then. Thank you so much for joining us tonight.